All right. Hello, everyone. My name's Liam, and I have a talk called Zero to RandomX.js, bringing web mining back from the grave. So here's me. So this is my GitHub. That's my website. It's not updated. I used to be a high school student. Now I'm here. I study advanced mathematics and computer science at UNSW. So my interests are compilers, systems programming, and WebAssembly in Linux, and recently like using Lean, so interactive theorem proving. So, but that's not what this talk is about, even though I would love it to be about. Yeah. So, all right. This is the purpose of this talk. So 1, introduce RandomX. 2, introduce RandomX.js. And 3, cover what's called the Semifloat implementation in RandomX.js. It's the reason it can exist. So it's RandomX. So this is an application-specific integrated circuit. It's incredibly expensive, incredibly specialized pieces of kit, which are designed to do exactly one thing and one thing only. So if you have a cryptocurrency and you want to basically prove that people do work, you need to do work on computers, GPUs, ASICs, right? The thing is, you want to get rid of these as much as possible. Because these enable centralization of hash rate, right? More hashes is basically your voting power within the network. If you gain more than 51% of hash rate, you basically control everything, right? It's 51% attack. So this is basically power, right? This is this puts the hash rate into the hands of the few who can actually spend the time to fab these and send these out. So these are highly specialized. They're basically for the few, really. So they're responsible for many 51% attacks on Bitcoin, for example. So once ASICs get in your network, it's basically over for miners using commodity hardware like CPUs and GPUs. So instantly, it only becomes competitive to use these. So Monero makes it their mission to only allow to only allow CPUs to mine efficiently in the network. So a CPU is a circuit, and that's also a circuit. So historically, this has been very hard. So how do you actually force people not making specialized circuits for your proof of work algorithm? So this is RandomX. So RandomX is a proof of work algorithm optimized for general purpose CPUs. So it stood the test of time as an ASIC resistant hash function. So on November 30th, 2019, they switched from their old proof of work algorithm, which was Kryptonite, to RandomX. And that point, ASICs for Kryptonite had already been created. So it was already been, their previous algorithm has been broken. So they needed it. So here's a quote from the README. RandomX uses memory hard techniques and random code execution. So random code execution, hence the name, to minimize the efficiency advantage of specialized hardware. So, the point is, you want the majority to get a fair shot. And in Monero's case, they chose to stick with CPU miners. What you want is something called egalitarian mining, basically where everyone gets a fair shot as much as possible, right? If I want to go mine, I just go to the store and I buy a rig. But not everyone has access to chip fabs. So this is RandomX on a high level. So that's supposed to be a CPU, and that's supposed to be 2 gigabytes of read-only fixed memory for it to sample from. So the hash function takes in 2 inputs, the key K, which is 0 to 60 bytes. That's basically fixed. And then you vary H, which is arbitrary length data. It's the data to be hashed. And it outputs a 256-bit result. That's R, so 64 bytes. So the intended use states 256-bit result, so that's 64 bytes, yeah. So the intended use states that you fix this key, so the key K is fixed. You build the data set from that, which can take multiple seconds. And then you use it like a normal hash function, so just changing H. So the only thing the VM will ask the data set for is to read its items. These things are mostly black boxes. These are decoupled from each other. As you can see in that corner there, that's the scratch pad. So it's a 2 kilobyte scratch pad. It's basically its working memory. The point of the virtual machine is to basically blast the scratch pad with as much entropy as it can. So blast the scratch pad with entropy, blast the registers with entropy, and then combine them both and hash them. That's the output. That's R. So, all right. So how does RandomX actually be ASIC resistant. It employs defense in depth. So RandomX opts to solve the ASIC problem with, a defense in depth. So you can't ban ASICs, they're just circuits, right? Because a CPU is a circuit. So the only difference between CPUs is ASICs are incredibly specialized with their circuits frozen to do a specific task. They're frozen. So our only weapon really is money. So remember, the goal is to use so many features from a CPU so that when it comes down to it, your ASIC will look exactly like a CPU. Then there's no advantage to fabbing your own. You just go down to the store, right? So what we want is something called economic infeasibility. So where the actual custom design and fabrication exceeds the cost of just buying commodity CPUs. So where you would, you would lose out to like 1, economies of scale, and 2, Monero could just change their algorithm. They could just change their algorithm. So it will turn your ASIC into a brick. So RandomX will tack on feature after feature to grow the cost of a custom ASIC. So first, ASICs that implement RandomX must have 2 gigabytes of external DRAM, and you need to be able to prefetch that. How we actually force ASICs to include memory external to the chip, it's something called memory hardness. That's a function of the data set. So when I explain the data set, it'll become clear to you why they're forced to do this. And we want random code execution. So, and these are the 2 obvious ones. So the goal is to force ASICs to include memory external to the chip and make the hash computation an actual random program, not fixed code. Right, so we already killed the ASIC part. So we want a superscalar design. We want ASICs to, when we implement this, we want something called superscalar design. We want speculative execution, and we want branch prediction. So CPUs are good at maximizing something called ILP, so instruction level parallelism. All of these things under superscalar design. So CPUs can execute multiple instructions at once. They can reorder them. They can rename registers. They can predict branches, and they can optimistically guess the result of some code. So all modern CPUs do this, and it's a huge advantage made up for how complex this is on chip. Like CPUs these days are incredibly complex. So if an ASIC wants to be competitive here, they need to factor in the cost of basically stealing trade secrets from AMD and Intel, right? There's no getting around this. Like this amount of complexity needs to be included on the chip if they want to be competitive. So that's a big thing. That's not a big thing. So 2 megabytes of scratchpad. 128. Yeah, it's 2 megabytes of scratchpad. On the previous slide, I had 128 kilobytes. 2 megabytes of scratchpad. So we have memory external to the chip, but CPUs have fast on-chip caches for frequently accessed memory, organized into an L1, L2, L3. So RandomX does use this, and it's where the VM sends all its entropy. All right, so we want full compliant IEEE 754. We want hardware SIMD, we want integer dividers, and then we want hardware AES instructions. So these are the things which are basically givens if you want to do useful work on a CPU. These need to be included. So the sum of all of these equates to a monumental amount of complexity and R&D time for a would-be ASIC. So creating one that does all of these would be prohibitively expensive. You'd just be making a CPU, right? So the goal is to accomplish these. So I'm going to explain the data set first. This is basically, we're entering the black box, which is the data set. So the data set is only considered with the key bytes k. So pre-initialization, so the key k is passed to something called the superscalar hash generator, which generates 8 superscalar hash functions. These are random programs, arbitrary code. The key k is also used to fill 256 megabytes of static memory. That's called the dataset cache. So the word superscalar is the key here. So what RandomX does to generate these hash functions is that it basically simulates a modern superscalar CPU to decide what instructions to emit to artificially saturate any host CPU. So the simulator takes an entropy and spits out instructions. And then dataset initialization, so we want the items. So each 64-byte dataset item is generated by executing each of those 8 functions and then zoring data from the cache, right? So if you want to mine fast, you can actually generate the entire 2 gigabytes up front. But if you want to mine on a memory budget or just verify someone's hash, like if you run a node on a Raspberry Pi, for example, you only need the 256 megabyte cache, as you can just run the 8 hash functions on demand. Use run one man. So this is called light verification or light mode, which is really the takeaway of this slide. So a would-be ASIC is forced to use external slow DRAM, right? 2 gigabytes. It's too expensive to put 2 gigabytes on chip, so it's forced to be external. And yeah, so so it would be expensive, and calculating the items on demand is extremely inefficient for even CPUs if you want to go fast. So either you include memory external to the chip, or if you put it on the chip or mine in light mode, it's going to be incredibly slow. So they're forced to include memory external to the chip. So the data set forces memory hardness on these ASICs. So, this is the RandomX virtual machine. It's only concerned with the H, right? These red lines, that's the data set. So it's only concerned with the hash bytes H. So on a high level, there are 4 main sections. That's the scratch pad, that's the working memory that we talked about. The program buffer stores the instructions. The register file is basically just the registers. And that's the abstract virtual machine. It's just the description of how to execute these things. Okay. I don't even know. Yeah, I don't know. Okay, so I'll go through the general algorithm. So an initial seed is calculated by hashing the input, and then the scratch pad is entirely filled using random bytes from the seed using AES. So next, the program buffer is filled, which is basically all the state needed to program an instance of the VM. So 128 bytes are set aside for the register file, and 2048 bytes are set aside for the program buffer. The VM is actually executed with all of the instructions, filling up the scratch pad and the register files with entropy, and reading from the data set. So every instruction that can read or write while it's executing will do so respecting the hierarchy of the scratch pad. So accesses to L1 are done 3 times as much as accesses to L2, and accesses to L3 are done sparingly and at certain times to avoid stalls. So after all of that, after it's executed, the register file is hashed and copied as state to generate an entirely new program, going around steps 3 to 5 again, where the entropy of one program is used to generate a new one, and so on. So we have 8 programs in a chain. So after we executed those 8 programs, we have a scratch pad, which is just completely filled with entropy. And then we hash it with rounds from AES, which is the final result. Yeah, and then the final result is the hash of the scratch pad with the register file. So you hash them both together. So the reason why we execute 8 programs in a row using the entropy from the previous one to generate the next one and so on is to avoid miners from re-rolling for easy programs, right? If you abort halfway through, you'll throw away all of your previous work. That's why we chain them. All right. So the virtual machine has 8 integer registers and a total of 12 floating point registers split into 3 groups. So the integer registers are 64 bits wide, and each floating point register is 128 bits wide. So these are SIMD registers. These are pairs of doubles. The FP registers A0 to A3 are fixed after programming. So F0 to F3, E0 to E3, they change throughout program execution. So the integer instructions are pretty standard. So addition, subtraction, multiplication, and the imul_h and ismul_h is multiplication and taking the high bits. Because if you multiply two 64-bit numbers, you get a 128-bit result. Takes the high bits. Yeah, so note that most of these instructions have _R and _M variants. So these either read or write registers or read or write memory in the scratch pad. So, all right, so here are the floating point instructions. So the only floating point instructions that are included are the base deterministic IEEE 754 instructions. So add, sub, mul, div, and square roots. And then we have like swapping a pair within a register, that's fswap. And then fscal, which is just equivalent to XORing the binary representation. So these are the MISC instructions. So stores into the scratch pad are just done with iStore, and then loops are implemented using cbranch. So the CF round instruction basically adjusts the value of FPRC. It's just that register there. which is the rounding mode of the core IEEE instruction. So I'll get to that in the next slide. So that's the basically the VM in its entirety. So before I conclude this section, I want to go over floating point numbers because this is really the point of this talk, and give an explanation of why RandomX would even want to use these, given that they have a track record of feeling non-deterministic or random. So here's the most common example, right? You might have seen this. 0.1 plus 0.2 is not 0.3. So this sets a lot of people off because this is not what they should be expecting at all. So the point is that floating point numbers like IEEE 754, they make a trade-off between performance and ease of use over actually representing the numbers they represent. So for IEEE 754 doubles, you get 2 to the 64 possible numbers compared to the infinite amount of real numbers, right? So what is R? R is a double, it's a set of doubles. So it's a finite amount of useful numbers with plus or minus infinity. So this is just simplified. We're not considering nans or subnormals. So because we lose out on the ability to represent an infinite amount of numbers, we don't have, for example, associativity. So this function will almost always return false unless you're working with integers and certain well-formed numbers. It'll almost always return false. So the point is that the function is doing rounding at different stages. So if you look on the right and you take that little circle function to be rounding, it's like pretty obvious where the rounding's happening. It's either happening on the left or happening on the right. So yeah, the difference is pretty pronounced. So, but I haven't actually addressed the elephant in the room, which is that programmers think that working with floating point numbers, like they find it frustrating, they find it inaccurate, it's basically a random black box. I know Max over there. So if floating point feels inconsistent and like magic at times, why should RandomX rely on it to give consistent results, right? Is it portable? So it is well defined. So floating point numbers are perfectly specified with addition, subtraction, multiplication, division, and square roots correctly rounded. These are your 5 core operations in IEEE 754. So what does correctly rounded actually mean? So basically, you take 2 numbers, you do an operation with infinite precision. So how it's defined is you have 2 floating point numbers, you add them in the real numbers, and then you round it back down to a floating point number. So you have 2 numbers, you add them, and then you round them. So the 5 core operations of IEEE 754 are actually defined this way. Anything else, like compound operations, so like your sine, exponential, these behave differently on other platforms, right, with different math libraries. So you can't expect them to be portable, or yeah, you just got to get lucky if you don't bring your own. So and there are actually 4 different ways to round a number so that it goes back to being a floating point number. So you have round to nearest, round down to negative infinity, and round up to positive infinity, and then round towards 0. So I'll give a proper explanation next slide. But if you do any of these 5 core operations on floats, right, if you add 2 numbers, how does your CPU know what to round them, like what rounding mode to use? So you can expect your CPUs to round them according to some inbuilt register inside your CPU. It selects a rounding mode globally, not per instruction. That's important. So in RandomX, FPRC is this register. So what you need to take away from this slide is that floating point numbers are perfectly defined and portable. They just have a decent amount of internal machinery to do with rounding and a lot of foot guns. But there is a caveat though. You only ever get access to Rn in most programming languages. These things, RD, RU, RZ, these are called directed rounding. You don't get access to these. It's usually a low-level thing. So, all right, so to expand on this, these are code snippets in C, JavaScript, and Rust. So in those languages, it is always assumed or forced to use Rn behavior. So this is generally what you expect for any code, for like 99% of code out there, which isn't a scientific library or like, I don't know, something at NASA or something. So 99% of code out there. So Rn has a lot of nice properties for over-directed rounding. So it accumulates less error and has less bias. So those directed rounding, right, RD, RU, RZ, these are your like low-level operations. So if you actually want to use these, for example in C, without invoking UB, you need to let the compiler know not to optimize with the assumption that the global rounding mode is Rn. So they use a pragma there. So for the add function on the right, it actually has the semantics of using the actual dynamic rounding function that is decided by the CPU, or whatever implementation of FP you have. So we're calling back to the first slide. So so this is the reminder. So the goal is to make ASICs resemble CPUs. So this is what an ASIC needs to do. It needs 2 gigabytes of external DRAM. It needs random code execution. It needs a superscalar design. It needs full compliant IEEE 754, hardware AES, dividers, SIMD, and 2 megabytes of cache, right? What does this look like? This is a CPU. So verdict, there is no advantage over a CPU. It's economically infeasible. It's just straight up irrational to make your own. So this is success. So RandomX is probably the most successful anti-ASIC hash function ever. Like, it's very over-engineered. Well, you might think so, but it's actually, it has the right amount of engineering, right? I mean, in my opinion. So here's my implementation. So I'll just talk about web mining. So Monero has a certain relationship with web mining. This web mining is just executing a script in the browser to mine coins at your user's expense. So it could replace ads, but this is just used for cryptojacking websites. So this is basically like installing a script in a website that you hacked into and then mining without them knowing. Like, this is a crime, it's bad. So for example, right, the Pirate Bay, to gain some extra revenue, used a service called CoinHive. It's just a company. And they put a script tag in their website, and it just mines Monero. So CoinHive as a company basically disappeared into thin air around the same time RandomX came to be. They just killed. Web mining was killed. So since then, there have been no serious or working implementations of RandomX since its introduction, and really suggesting that one could be implemented is actually quite laughable in the Monero community. The question is why? Yeah, so the question is why, right? Why would it be laughable? So this is a quote from the README. So does RandomX facilitate web mining? So web mining is infeasible due to the large memory requirement and the lack of directed rounding support for floating point operations in both JavaScript and WebAssembly, right? We're stuck with RM. So all of the memory requirement stuff, right? I mean, we can just use light mining, right? But for floating point, they do millions of those a second. If it's slow, at least a little bit, it's useless. But we're stuck with RM. So how do we get the 3 that we need? So Tevador, the creator, thinks it can be done, just really slowly, which he estimates 30 hashes a minute, which is less than 1 hash a second. So really, that's just really low. That's just really low. So I wanted to try and beat that. So here's a quote from my README. So RandomX is an implementation of the ubiquitous Monero POW algorithm, RandomX in JavaScript. So the question is, like, why would I attempt this? I don't really care about web mining. I just think it's an interesting problem. So first, what would the code actually generate, right? So like in RandomX, you generate machine code, right? Would I generate JavaScript? That probably wouldn't be fast. So instead of generating JavaScript code, you can do something much closer to the JITs and the actual RandomX. You can generate WebAssembly. So 5 years later since RandomX was introduced, we have WebAssembly now. So it has SIMD and shared memory. It has threads. It's really expressive. You get branch tables, and you get like memcopy and all of these things as built-in instructions. So the point of WebAssembly is to be a compilation target for performative sensitive code. So it's basically assembly for the web, where you work with raw memory, unboxed integers, and so on. So JavaScript can execute arbitrary code at runtime. You just need to generate WebAssembly and then get JavaScript to load it and execute it for you, all right? But there is some downsides to working on the web platform. So you don't get AES, you don't get the through rounding modes like we talked about, and it's like you also like can't allocate 2 gigabytes of memory. Like a web page just can't do that. That's just irresponsible. So we're stuck to light mining. So what we can allocate is 256 megabytes. We can do that. So it's an overview. So RandomX.js is a complete rewrite of core RandomX. So it's in C++. I rewrote it in C. It's 5,000 lines. It's 500 lines of host glue TypeScript to actually execute the WebAssembly. It has the same tests as RandomX. It's 200K line of code test suite for the floating point implementation. And it's really like kind of the only readable implementation in existence. The original C++ was like template hell. So it just wasn't good. So there's no hands tied behind my back. Like there's no interpreter here. So the RandomX code is generated. So WebAssembly is generated and executed by JavaScript. The cryptography has been rewritten to use WebAssembly SIMD. We have performance-directed rounding. We get those through rounding modes using something called Semifloat. And then it also has support for shared memory and threads, right? If you have a thread, multiple threads, you want to share the cache because it's immutable across them. So how's the performance? So naively mining in a loop, 22 hashes a second. Naively mining on all the threads, 210 hashes a second. So I mean, that's pretty slow, but on the same machine, I get 100 hashes per second on the same thread, right? So 5 times slower is pretty good. Like that's pretty good given what I'm up against. So I'd consider this a win because it's just much better than the 1 hash per second figure speculated by Tevador. So here, so this is the motivation behind what I'm going to explain next. So during the virtual machine execution, a branch table, so there's an instruction called call indirect in WebAssembly. It selects the correct floating point operation with rounding. So it basically selects the right function. So fadd_r has 4 implementations. It has fadd0, fadd1, fadd2, fadd3 for rn, rd, ru, and rz. So the thing is, though, we're stuck with only one rounding mode rn. So how do you actually implement fadd1, 2, and 3, right? You don't really have a solution, so we're kind of stuck here. For example, on the left, here's like an implementation of fadd0. It's actually ripped from the source code. You just add them. It's just super simple. But to answer that question, like to answer that question, we'll actually go over how it's implemented in RandomX.js. So we're going to go on a deep dive. We want to beat this goal. So this is Semifloat. So how does rounding actually work? The easiest way to show this is with a picture. This is a number line. These are the real numbers. On that number line, there are little ticks. These represent the actual tangible floating point numbers. So we have that RD, for example, RD is trying to pull a number as far as it can to negative infinity. RU is trying to pull it to positive infinity. RN is trying to pull it to the nearest tick, right? And then RZ is trying to pull it towards 0. Basically, on the number line, you have these ticks. If a real number lies between them, the correct rounding mode, a certain rounding mode will snap it to those ticks. So there's a definition here. So unit in the last place, ULP, is the gap between 2 floating point numbers nearest to x. This is a definition by Khan. So if we look at our diagram, right, our floating point numbers, these ticks, do have a semi-common distance, at least the close ones. So we have that, right? Each floating point number, each tick, right, is at most 1 ULP away. So rounding functions can either snap up or snap down. You can't snap any further. There are only 2 places to go. So can we use this to our advantage? So we're going to try and use this fact right now. We're going to try and derive something. So take some x. X is a real number. So we have that x is equal to its rounding plus some error, right? That just intuitively makes sense. If you solve for epsilon, we have that if epsilon is 0, the operation was exact. If we have that it's less than 0, we round it up. If we have that it's greater than 0, we round it down. So what's the upshot? So if we can find epsilon, even just the sign, we only care about the sign here, we can detect when rounding happens and correct it. So imagine some function called rn star. It basically takes in a real number and then returns the rounded value plus the epsilon error, right? If you just sum them, you get back to the input. So rn star doesn't exist in general. It just doesn't exist in general. But like, let's imagine we had it. So just for summing 2 numbers, let's just imagine we had it. So if we wanted to implement fadd1, we could just use rn star here to find the error and then snap the sum to always rounding down, right? For example, epsilon's less than 0. We round it up, so we need to round down. Else, it's exact, or we already rounded down. So that's good. That's how we implement round down. That's basically the entirety of Semifloat. So this algorithm does exist. It's called toSum. So among many others, these are called error-free transforms. These are EFTs. This is basically your rn star here. So this is something we can actually compute. We can actually write this down. But if you don't believe me, here is the actual C code that does this. So there are no hands behind my back. This is an actual implementation, and it's similar to what RandomX.js uses. So next after is a function in math.h that basically gets the next representable float in the direction of the second operand. So you're just minusing ULP there. And though, right, you're counting like 1, 2, 3, 4, 5, 6, I think, is that 1, 2, 3, 4, 5, 6, yeah, 6 operations, one branch, that's definitely going to be slower than just adding them, right? And it is slower, right? But how slower? That's the question. So it is slower, right? But what is the alternative? What if you didn't have this? I'll show you, and the alternative is much worse. Much worse. So I'm going to make a couple of definitions. So a floating point implementation by hardware is called hard floats, hardware float. Floating point implementation by software with integer operations, these are called soft float. So the motivation behind that is like, what if your CPU doesn't have an FPU, but it just has integer operations? You can emulate floating point in software, right? This is also useful for kernels. So what is this thing called? What is this thing that we came up with, right? What is it called? So it doesn't have a name, but in vain of these similar definitions, I'm just going to call this Semifloat, and I'll just like name that for the rest of the talk. That's the name of it. So now, is Semifloat any faster than these three? So on the left, that's hard float. We're not beating that. It's the fastest. But yeah, but on the right, here is the actual Semifloat implementation. So this is basically what we had on the previous slide. It's just using WebAssembly SIMD. It like kind of obfuscates the code a bit. That's why I didn't show the SIMD version. But it's basically the same. And this is a branchless next after. So we can't beat hard float. So it's Semifloat versus soft float. But we don't know what soft float looks like. So we'll take a look at how it's going, and we'll benchmark it. So this F64 add is taken from Berkeley softfloat with the actual implementation modified to be as fast as possible, given RandomX's assumptions. I'm really being as charitable as I can. So I've removed as many branches as possible. So to start, the softfloat implementation checks the sign and then dispatches to a function. So, and if you look here, right, as a branch is branch, right? What else? There's like a branch there, and then you do the rounding. So many branches could be eliminated given the assumptions, but not all of them, right? So we're left with this, and it's like pretty ugly. So the reason why there are so many branches is because floating point addition needs to basically align the floating points and then sum the values. In general, this is a pretty involved operation and basically completely unpredictable. Like these branches are completely unpredictable, which makes it slow, makes it very slow, but we'll see. How slow really? So I did a benchmark. These are G-flops here, so higher is better. So this is a benchmark I tried on a couple CPUs, a couple of you guys are CPUs. So these are modern, out-of-order superscalar CPUs. Generally, you can expect the operations with the least unpredictable branches to win here. So because toSum doesn't use any branches, right, our Semifloat implementation, the CPU can basically execute both the calculations for delta A and delta B, as you see in the residue. So it effectively goes down from 6 floating point operations to only 2 to 3, really, when it comes down to it performance-wise. So the overhead is really only 2x, so that's not bad. That's pretty good. The soft float, though, that's 17 times slower compared to baseline, 17 times. So those branches hit hard. That's as expected, though. That's as expected. So, I mean, we're beating soft float by 10 times. I guess that's the reason. why Tevador said 1 hash a second. I guess that's where he got the numbers from. So we'll take a look at multiplication. So this is the Semifloat implementation of multiplication. So it's structured very similarly to the Semifloat version with addition. So I'll just go through the parts. So the top is the same. You just calculate multiplication. You just calculate the multiplication. The middle part is where we find the error. So there are calls to frexp and ldexp. These are just functions in math.h. Basically, the point of that is to scale the 3 values. Basically, we're scaling them equally. And then we're calling mul residue to find the error. So even though we're scaling them, we do change the value of these numbers. But the thing is since we perform equal scaling, it doesn't affect the sign, and we only care about the sign. We only care about the sign. So, yeah. Oh, shit. So we do have infinity for the E registers, right? You get infinity on multiplication, division, and square roots. So we need to have this branch here, but it's a rare branch, so it costs next to nothing. So this branch is actually okay. And then finally, it's fed into the same next after function for summation. So it's very similar. We just have that mul residue is just like swapped out with mul sum, the other one. So what does the mul residue actually look like? This is one of Decker's algorithms. It's another EFT like 2-sum. So this whole thing is still branchless, but I mean, it's very ugly. There's like more than 15 floating point operations in here. So it must be much slower than addition, but we'll benchmark it, we'll see. So, but there is this note here at the end, right? At the end of this huge computation, we basically get the variable a times b and subtract it with c here, right? This is the core of this entire function. The whole point is to find a times b minus the rounded value, right? That's what we had before. That's the residue. That's the epsilon. So we just want to extract epsilon. So is there a way to skip all of this crap here? Is there a way to skip it? So we'll look at this deeper. So we're actually trying to derive something like this. So starting with what we know, we want to find an equation, like a closed order equation for epsilon. So remember that the real value, a times b, is actually the rounded value plus some epsilon. So we'll define c there. So we'll solve for epsilon, which is basically, you get a times b minus c is just epsilon. So it's pretty intuitive. We haven't really done anything crazy yet. But what we can do now, though, is we can apply Rn to both sides. So we'll apply Rn to both sides. And, well, that Rn epsilon is equal to epsilon, right? Why? Because epsilon's already a floating point number. So as you can probably see, the easiest way to find basically a closed form solution for epsilon is you have to multiply a times b minus c in infinite precision and then round at the very end. So we don't really have an operation that has this, right? So is this even possible? Right? Is there a way to do a times b minus c in one rounding? So IEEE 754 2008 specifies add, subtraction, multiplication, division, and square roots, and FMA correctly rounded. So what is FMA? So there's a definition. Fuse, multiply, add basically calculates a times b plus c, then does a rounding at the end. So it's one rounding, not two. So it's not a double round. If you implemented it like this, like the naive way, like you just wrote it out, multiply a times b plus c, you end up with two roundings. This is not what you want. We'll get a different epsilon. So now, though, the code here, if we actually use this, it looks super simple, right? All we do is perform a times b minus the floating point value of a times b. And that's it, right? We can even skip the infinity check because it's handled for us, which is nice. So this is why, hands down, like FMA is my favorite instruction. But it's not on all CPUs. I mean, it's on all modern CPUs. So here's the benchmark again. So the orange software multiplication, it's down there, isn't 10 times slower now. It's like 4 to 5 times slower, which is pretty tenable. The red is the hardware there. So remember, it's the same thing. It's G-flops, higher is better. So the green semifloat with FMA here, though, the green, is like, it's absolutely the best here. It's absolutely the best option. It's only 80% slower than baseline hardware, which is pretty good. But it seems like here, the blue, the naive semifloat with the 15 floating point instructions, it barely has the lead it has before. But so the software implementation, the orange, is very close behind. It's still faster, though, except for that CPU. Just ignore that one. It's still faster, though. Even with naive semifloat, the blue, doing 15 floating point operations. So what happened, really? So this is the Berkeley softfloat version of F64mul. So the thing is it's so small that it can actually fit in one slide. So like the F64 add softfloat version, I optimize it as heavily as I can, given the assumptions. So remember that floating point addition is much more complicated in terms of branches. So because you need to align the floating points, that's why it's slower. So a super simple example is as follows. So take two floating point numbers, a and b, you multiply them. If you multiply them, you just sum you multiply the mantises and then you sum the exponents. It's super simple to do in software. It's much more complicated to do in hardware, but we have multiplication and addition in hardware. It's just integers, right? So in short, let me give a short summary. So RandomX forces non-trivial floating point rounding to maximize die space on an ASIC, just to maximize it. WebAssembly, JavaScript, Rust, Python, just all these programming languages, they only have access to Rn. So what do you do now? We can use these things called error-free transforms, EFTs. These allow you to implement round down, round up, and round zero in terms of Rn without using a slow software implementation. So this speeds up the emulation of addition considerably, and multiplication just a little, but they still win. So I guess we learned that the bane of slow software implementations is unpredictable branches. So the cost of multiple floating point operations still is much lower than the cost of a single unpredictable branch, which is pretty funny. So this allows RandomX to be fast, right? RandomX.js to be fast. So I'm going to finish up, and yeah, so thank you, everyone. It's Q&A time. This is references. It's a bunch of URLs if you want to read, but anyway, thank you. Thank you. Question?
I am very curious about your, what you were saying with the branchless performance, because to my knowledge, usually that's something that a compiler would be very good at optimizing. So is there a reason you had to create those optimizations manually? What are the limitations of, do you know much about the limitations of the compiler optimization?
Yes, so I had to cut some stuff due to time. So RandomX, the only reason why this is possible, right? The only thing that Tevador needs to do to kill everything is to basically allow subnormal numbers in floating point. These are numbers that are very close to zero. Basically, there are many assumptions in RandomX. So, for example, addition, or for multiplication, there's no negative numbers, no zero, you're supposed to have infinity, things like that. The reason why I could eliminate those branches is because I just delete the code that says, is this thing infinity? Yeah, that's it. So the compiler has no idea.
It's stuff that you can safely assume
Yeah.
that an ordinary compiler would not be able to safely assume.
Yeah, the compiler, yeah, it wouldn't know. Yeah.
Perfect.
Yeah.
Yeah, so you said, you made a point about RandomX.js needing to be in light mode because you can't get 2 gigabytes of memory.
Yeah, that's the thing, yeah.
You can, come on.
You can. People have told me you can, and then they said even if you can't, split it into 2 different allocations, which you can do, but it's
It's overhead at that point.
I mean, it will not really. The thing is, the overhead is actually generating the data set. So generating the cache takes a couple seconds, but generating the data set, I haven't tried, but generating the data set on JavaScript and stuff, it'd be so slow. It'd be 15 seconds.
Yeah, also, you kind of touched with that on the previous question, but if you could make one change to WebAssembly, JavaScript, or even the web browsers running the code, that would just absolutely skyrocket the performance of RandomX.js. What would you change?
There's a couple things. So I want hardware AES. The thing is the SIMD thing is already in there, so you can't change it, which is annoying. So I want hardware AES. Really, the biggest issue to my performance is probably, so when you generate WebAssembly, the JavaScript engine has to convert it into machine code, right? So basically, I'm basically at the whim of these engines to basically generate this code quick enough. So I get no optimizations, I checked. So I get something called the baseline JIT. I get the baseline JIT, so it's just a really naive translation of my JITted code into machine code. So it's just, I don't use, it's not optimized at all. So there was just loads and stores everywhere all the way down. And there's 2,500 instructions, I'm guessing. Probably, the thing is I would change WebAssembly to be more low level. But yeah. That's kind of the biggest thing.
Yeah, I mean, the crutch on the reason why Semifloat had to be implemented is because you cannot specify the rounding modes, right? If who would you need to have changed their implementations, their frameworks, whatever, to just directly be able to
access the rounding modes?
Yeah.
So generally, that's really hard to specify. So all the languages that I mentioned, so Rust, C, C++, all of these other languages. The thing is, the floating point rounding modes, the FPRC, like for example, x86, it's not named that, but it's similar. It's global. It's like just global. So the thing is, all compilers, they optimize with the assumption that only Rn is used. So you don't touch this global state, this global variable, you don't touch it. So generally that's really, really hard to specify. And WebAssembly just doesn't, Rust just doesn't, C just doesn't without a pragma, C++ just doesn't. It's generally like hard to specify because it's a global variable, you know.
Do you know of the circumstances where like it could be a boot like kernel thing, a boot runtime, where the global like rounding mode will be changed, and can you influence that in any way?
So,
any CPU you've tested?
like for example, for me and JavaScript,
Yeah.
No way, it's sandboxed. There's nothing you can do. Yeah, sandboxed. Yeah.
Okay.
Anyway.
But it's something that you would be able to do in regular C.
Yes.
Would like 2 rounding mode switches be slower? Because you could like very easily like specify allowing the user to switch a rounding mode for the next instruction and then switch it back to normal to continue off.
But the thing is like in WebAssembly, I don't get access to the internal FPU state.
Oh no, but I'm talking about like.
You mean like that little example?
No, like going off what Josh said.
You mean like in RandomX?
In the ideal case, we
Yeah.
can change them.
In the ideal case, I just implement it the exact way RandomX does if I have access to the FPU state. I just copy RandomX. Like, yeah, I just copy it.
Any more questions?
Questions? Max, got a question?
So two things. One, did you achieve fast enough web mining for crime? Asking for a friend. Like, is this practical enough that I could put it in, say...
It's actually very practical. It's actually very, very practical. Like, it's like beyond their expectations. It is practical. And for example, like, it's not just like one CPU. Like, for example, anyone can just open their phone. So you get like 100 people. Anyway, I don't really care about web mining. Some people here do. But yeah, it's actually beyond practical. Yeah.
Got it. And my second question
Oh, well,
is,
actually, yeah. Anyway, go away. Yeah.
I know Ruby lets you specify the floating point rounding mode.
Oh, can you?
Yeah.
Seriously?
Yeah. So, given that, would a Ruby implementation ran on Truffle VM be blazing fast?
I'm gonna be on the perf. Okay. I think it wouldn't be that bad because you also get baseline JIT and Truffle. I think it like you could just give it a go. It will be fun. You can. I say that you can. Yeah. Or you can just compile to C. Anyway. Yeah.
It seems like a good holiday project.
Right. I think that's
Any more questions? All right, we'll leave it at that. Thank you very much.